All right, welcome everybody to the TerraSource Global Web Series. Today's presentation will be on pneumatic conveying. My name is Kyle Hoffman, and I'm an applications engineer for the Jeffrey Rader brand of TerraSource Global. Also includes Pennsylvania Crusher and Gunlock. So what is a pneumatic system? A pneumatic system is simply a method of transporting material on a moving airstream. You have a blower that generates the air. Should be inlet and discharge silencers to reduce noise level and tame pulses. Material is introduced to the piping with the ESW feeder. Might include a diverter valve for multiple discharge points. Should have some elbows in the system. Might have a cyclone that's useful for discharge into a bin. And you might also have a deflector nozzle which blows into a pile. These are just some examples. We'll get into some of those other discharge devices later. So here's a graph that shows the pressure and velocity profiles within a system. Jeffrey Rader designs dilute phase high pressure systems. You'll notice that the pressure starts at a maximum and then decreases as the system goes until it reaches zero at the end. And then velocity starts out and increases until it reaches a maximum at the end. This top curve here is for the air velocity, and this lower curve is the matching material velocity. Notice the difference between the air and material at each feature. This up here shows the feeder where the material enters, and it quickly accelerates to conveying velocity. And at that same location where the material is accelerating, you'll notice the steepest pressure drops. This is due to acceleration loss, which is the energy required to accelerate material from rest. And this is one of the biggest pressure losses within a system. You also have friction between air and material and the pipe walls. This is shown in these longer drops. Velocity is going to keep increasing following all these curves. So the positive displacement blower is going to deliver a constant volume of air. Inside that blower, you have impellers rotating at close clearances to the housing for maximum efficiency. There's the housing. Over time, those clearances are going to increase, which reduces the efficiency. You might have to rebuild the blower at some point. We'll also include controls to monitor the conveying pressure. If the conveying pressure gets too high, the infeed will stop, but the blower continues to clear the line out from the material. If it stays high, then the blower will also stop because the line is most likely clogged and have to be manually inspected. We also include a built-in check valve in the discharge air piping that automatically closes when the blower stops, and that prevents back pressure from carrying material into the blower. We size these blowers based on the CFM and PSI requirements within the system. That, coupled with the maximum RPM of the blower, is what's going to allow us to choose the right one. Typically see pressures around 6 to 8 psi gauge pressure within a system. It's going to change unique to each system. And then initial velocity might be around 105 feet per second. It's going to be different with each material, and as we said before, it's going to increase to a maximum point at the end of the system. You have inlet and discharge silencers. These are very important because the compression of air in a blower creates noises and pulses. So the noise, is uncomfortable, and you'll need to lower it to within OSHA standards. You might damage some equipment around the blower without these silencers. The other important part about a discharge silencer especially is that it's able to tame the airwaves. With large blowers, it's more of a pulsing action coming out of there, and so that discharge silencer will collect that and allow for a nice smooth discharge of the air and prevents pulsing in the system. You want to have a nice smooth, or as smooth as possible, volume of air going through to convey that material. Our ESW feeders are designed for continuous duty service. You have a top knife which shears any material that hasn't fallen completely into the pocket. The rotor carries material around and then out of the bottom flange. Any material that doesn't completely fall out is sheared by the bottom wear bar, and this bottom wear bar also protects the chrome liner of the feeder. Rotor tips are hard-coated. The industrial housing, as we said just a second ago, is chrome-plated. That is able to extend the wear life of the feeder, also provides corrosion resistance. The rotor and housing are machined to very tight tolerances, and this allows us to minimize the air leakage from the feeder, and that's taken into account when choosing the blower. Over time, that clearance between the housing and rotor is going to increase, which will create a greater leakage. You can readjust sealing rings and readjust the top knife to extend the wear life. Beyond that, you're going to have to replace or rebuild the feeder to continue working at maximum efficiency. ESW feeders require a metered in-feed of material. It needs to be controlled. It's not really a feeder in the true sense of the word. It's more, think of it more like an airlock that just introduces material to the high-pressure conveying system. We never designed feeders to operate at 100% full. The ideal fill rate for us is around 40 to 50%. Anything higher than that is possible, but it will lead to premature wear and replacement of the feeder, which isn't ideal. And that is the reason why we need that metered in-feed, so that way we can maintain that steady rate of 40 to 50% fill in that feeder. Feeders are sized based on volume, using the maximum possible feed rate. You know, we don't really want to have surges in the system, and if there are going to be surges, we'd want to design the entire system for that surge rate. One other thing to think about is that the max particle size in your system, we'll just want to make sure that it's not larger than the pockets in the rotors. You don't have excessive shearing in the top knife. But that's something we'll check out. Here's some piping. Got mild steel all the way to abrasion resistant varieties. It's better to run horizontal and vertical than at a slope, as is shown in this picture. When you're running at a slope, gravity is acting on the material, and it's going to increase the friction. Kind of think of it as the material is going to be bouncing in a stepping pattern up or down the slope. And it's just not good for the system. When you're running with just horizontal and vertical pipes, it creates less friction, fewer pressure losses, lower horsepower, saves you money. Here's our Mark III elbows. They're designed to reduce energy consumption, reduce wear, and eliminate fiber damage. The material is going to hit the 10-degree impact area down here, and it's going to be guided smoothly as it changes direction until it discharges at the center of the downstream pipe where air velocity is maximum. It allows the material to get re-entrained to the system most efficiently. As you can see over in this image, the high impact areas are easily removable and replaced. We also offer proprietary blends called R35 cast segments, which are extremely wear resistant. It's not an exact thing, but it will typically see 6 to 8 times the wear life of AR200. Kind of gives you a frame of reference. You don't want to be changing these things out very often. It's just more downtime, loses more money. Also have diverter valves, allows you to redirect the pipe to multiple locations. We've got 2 different types of valves here. It's the 09 valve, which moves in 10-degree increments, and G valves, which move in 7.5-degree increments. They're similar, but have their differences and have their advantages in different scenarios. Offer these valves in both manual position system or an automatic positioning system, which uses gear motor drives and limit switches to change that pipe. As with the elbows, these valves also include low impact angles, which help minimize the wear, minimize the pressure drop, minimize horsepower. These are going to be important themes throughout pneumatic conveying systems. Here you see a few Model E cyclones. So a pneumatic system conveys material in a large quantity of air, and you need to separate that air out before you discharge it into a bin. These cyclones, just as with the valves and the elbows, are designed to have low impact inlet section that allows you to minimize material damage, eliminate buildup, and longer service life, easier maintenance, all the important things. Got different options. You can do multiple injection as shown in the photograph on the left. You can do right hand, left hand inlet. You can replace body liners, though most people just choose to replace the entire cyclone since they're comparatively inexpensive. So the way this works is that the air-to-material mixture enters a cyclone, then it spirals around the body of the cyclone very quickly, but the velocity is going to decrease because of the friction. Material is held against the sidewalls while the air begins to move inward. Material keeps on slowing down until it reaches the bottom, and it drops out in a spiral motion out that discharge port. Air does the same thing, though it moves closer and closer inward, tighter and tighter spirals, and when it hits the bottom, instead of going out, it shoots up the top and out that center top hat that's shown best in the center picture. It just releases the air to atmosphere. Sometimes you have environmental concerns where you don't want to release the air to atmosphere, and in this case you can have it released to a cleaning device, or in this image show a secondary cyclone. So there's the primary, and then there's the secondary cyclone. Material with a high fines content is going to benefit from that secondary cyclone. The additional cleaning of the air helps out. You notice the secondary cyclone has a long cone compared to the primary cyclone. These long cones offer greater separation efficiency, which for high fine content or dusty material is going to be very important. Here's a target box. The way this works is you have air and material entering here. This blind flange at the end allows for an area for the material to build up and provides an impact area, and then the air and material discharges out the bottom into a bin. Since there's no separation of air and material with this device, you need to have some sort of vent in the bin to prevent an explosion. Also, since that material creates an impact area, see an extremely long wear life with this because there's really no wear areas in it. Just to finish up the discharge devices, here's a deflector nozzle. Allows you to blow directly into a pile. Creates a pretty big mess if it's sawdust. And here's direct inject. If you're doing a boiler feed, you can directly inject into a boiler. All we need to know is the operating pressure of that boiler, and we're good to go. So what can we convey? Really almost all types of materials. Wood products are going to be your most common. Wood chips, sawdust. Also do charcoal, wood waste. Really, if you can think of it, we have a chance of conveying it. Old corrugated cardboard, municipal solid waste, among others. Preferences with dry materials. 70% moisture is sort of the cutoff level there. It's also possible to run several different materials through the same pipe. What we would do is design for the worst case scenario, and what you would be doing is just wasting horsepower when materials are able to convey smoother. Basically, we at Jeffrey Rader have got 50 years of experience conveying these materials, including over 1,000 installations worldwide. So no matter what your application is, there's probably a solution. So what do we need to be able to give you a pneumatic system? We need to know the material type. This determines several design factors, including initial velocity, which we'll go over in a minute. All these specifications are critical because they define a unique system. If anything's changed, the system will not work properly. We would need to know about it so we can make necessary upgrades or changes to the system. The rate, don't want to guess on capacity. If you overestimate, you're going to be wasting horsepower. You underestimate, it's not going to convey. We need density. Minimum density is going to determine the largest volume of material to be conveyed. That's going to give us the feeder size, among other pieces of equipment. Max density is going to dictate the highest tonnage to be conveyed, which helps us size the blower and pipe size. We'd like to know the maximum piece of material, and that goes back to the feeder discussion. An 8-inch piece of material won't fit through a 6-inch pipe. It's as simple as that. We need to know the horizontal and vertical pipe length. We do not need to know an exact layout. We really just need the overall horizontal distance, the overall vertical distance, and the total degree of bends. Don't need to know there's 490s. We just need 360 total degrees, and we can get a very close estimate to what you need. Temperature and elevation are very important. It's going to affect the air density. As an example, air at 2,000 feet is going to be 7% thinner than at sea level, and air at 100 degrees Fahrenheit is about 5% thinner than at 70 degrees Fahrenheit. If you don't take this into account, your system might operate in the morning, but then not in the afternoon when it heats up. So a Jefferator, we always make sure that that is accounted for. You need to know the number of in-feed points. Typically, you'll have one in-feed, but you can do multiple injection points. In this case, we do need to know the exact location of each feeder, since there's going to be different rates delivered at each location, and that is going to be an important factor for us. And then we also just need to know the number of discharges and the type. You've got a diverter valve that splits the run into two. Typically, the longest pipe run is going to be what's critical, because it's going to be, as we say, the worst case scenario, but we would like to look at all the piping runs to make sure that the shorter run doesn't have, say, a larger vertical section or more elbows, which would actually turn out to be the worst case scenario. And then the type of discharge is, of course, important, because there's going to be different pressure losses associated with each different type. So how do we put this together? Well, you tell us the material, and then we'll be able to tell you these factors: the minimum initial velocity and the minimum air-to-material ratio. These are both going to be starting points for optimization calculations and are going to change as we go through the system, see what's needed. We have friction factors that are based on 50 years of testing, basically, and this is going to help us determine the pressure losses between material and air and the pipe contact. Design rate is really a safety factor. If we have really difficult materials, we use a larger design rate, or if there's a lot of unknowns, maybe you don't know exactly what the tonnage is going to be, we'll use a higher design rate just to make sure it's going to work. Can also run these calculations based on existing conveying line. Say you have something in your plant right now and you want to increase capacity. We can take what you've got, run calculations on it, and test to see if you can increase capacity based on what you already have, or maybe what components need to be replaced. We can add a helper blower, add a brand new blower, both simple solutions to be able to reuse most of your pneumatic conveying system. So what does that tell us? System CFM is going to be important for our calculations. The differential pressure also going to be very important. Pipe size, obviously. Size of the cyclone required, the blower size, and the feeder size. Now, all these components are selected based on that given set of criteria and are unique to that criteria. If anything changes, the system likely will not operate correctly. The system's designed too small. Obviously, it won't convey the material properly or at all. You have material just sort of slugging down the pipe as pressure builds up behind it, then shoot forward a little bit more, and pressure builds up, and not efficient at all, increased wear. And then a system designed too large is also a problem, because you don't want to waste power, and you could have too high a velocity and the air just runs over the material. So in either case, it's very important to define a set of specifications and stick to them. A few things that are pretty important to consider. You want to try and keep the blower located fairly close to the feeder. It's possible to have the blower far away. A lot of times that's the only scenario, and in that case we just need to know the piping routing from the blower to that feeder so we can calculate the pressure losses from the air. Absolutely must have a metered feed of material to the ESW feeder. Since the pneumatic system can't handle surges, you either have to, if there's going to be surges in the system, we would have to design for those surge rates, because if we don't, when the surge occurs, the line is going to get clogged. So if there's going to be surges, it's a lot smarter and saves a lot more money if you're able to meter that with some sort of screw conveyor or drag chain. Something allows us to design the system for that design rate, saves on horsepower, you're not wasting anything. It's best to try and minimize the number of elbows in the system. It's pretty simple. Fewer pressure losses, going to lead to lower horsepower requirements, save more money over the long term. This one's important. You want to have straight pipe for 10 times the pipe diameter following an elbow or the feeder or any location where the material is going to decrease in velocity. And this allows enough length for the material to accelerate to proper conveying velocity after that elbow or after that feeder. Sometimes that's just not possible, and in that case we can create an accelerator to temporarily speed up the air. What's basically going on here is we choke down the pipe diameter, say from 16 to 15 inch, and the lower cross-sectional area coupled with the constant CFM is going to increase the velocity and help quickly accelerate that material, and you won't have any problems. It's going to be a maximum limit to the unsupported pipe length, and also expansion joints are pretty important for long systems. It allows longitudinal expansion of the pipe. Speaking of long systems, the expanded line concept is very helpful with these long systems because typically you're going to have higher blower pressure. If you remember back on the first or the second or third slide, the pressure decreases over the length of the pipe. So the longer system you have, the higher pressure there's going to be. And you like to decrease that pressure. What the expanded line concept does is the opposite of the accelerator pipe. It increases the pipe diameter, say, from a 16 to an 18-inch pipe. And that quick change in cross-sectional area lowers the air and material speed, which is going to lower the resistance to flow and, again, lower horsepower requirements. Lower velocity is also very helpful because it decreases system wear, and you definitely want to do that. Maintenance is very important. Extend the service life. If you have any kind of leak or hole, you want to make sure that you fix it properly. Scad patching is just not going to work because it's really just going to make the system get worse and worse. And if you want that system to run in full capacity, full efficiency, you want to inspect and make sure that everything is not worn. A lot of mills will rotate the pipes even to extend the wear life of their pneumatic system. A few advantages of a pneumatic conveyance system: it doesn't take up a lot of space. It's basically a pipe and supports. Can easily route around obstructions. You have a building in the way, you have trees in the way, you get right around that, no problem. You have limited moving parts exposed, so that increases the safety of the system and people working on the system. Along those same lines, pneumatic conveying is great for dusty materials, doesn't make a huge mess. Most all the high wear areas are easily replaceable. It allows maintenance to spend less time, less downtime. What we typically go by is at 250 feet, any conveying over 250 feet, pneumatic conveying is going to be less expensive than belt conveyors, and that includes the higher horsepower cost. This is not an exact number. You know, every system is going to be a little different, but especially in a system where several changes in direction are needed, pneumatic conveyance system is going to be the least expensive over the long run. So just wrapping things up, just pulling everything together, Jeffrey Rader can provide a full boiler feed system, and this is a great application for pneumatic conveying. You do storage, convey it, and then inject it directly into the boiler. As I said, all we need is just the operating pressure of the boiler And if you're interested in boiler feed, you can find more information on that on our YouTube channel. We've done a previous webinar presentation on that. And that's pretty much it. If anybody has any questions, now would be the time to do it.
Kyle, we did get one question in before anybody starts yelling theirs out. Based on the specific information required, is there an application data sheet that needs to be submitted with a customer's request for quote? And that's from Big Mike, one of our sales reps.
Yeah, Big Mike, that'd be great if I could. We've got application data sheets that includes all the required information that I went over. If they don't want to fill that out, it's not necessary. We know what we need, the density, the pipe lengths, but we can definitely get you a data sheet to facilitate that for you. Anybody else?
Yeah, can you tell me what you think the lower end of bulk density would be, or how light a material you would find this kind of unit useful for, or feeding your feed system useful for managing?
You know, it's going to be different with each material. We've got different density ranges. You know, it's going to be different if it's sawdust or if it's wood chips, but typically there is no lower limit on the density range.
So you wouldn't have any problem, for example, with cotton fibers or
cotton. Cotton might lead to other issues just in terms of anything that's real dusty around the feeder is going to create a mess. Stuff that's real light, you're right, like cotton, that could create an issue. But we don't really have any experience with it, so it's hard to say exactly whether that's possible or not.
What you have testing facilities for your materials, and I understand. What are the maximum rates that you can be putting through that in terms of airflow?
Well, again, that's going to depend upon the material and all those other factors, but we've delivered systems up to 1,000 tons per hour. It's really just going to be limited on, you know, what the required CFM and PSI is once we look at everything, all the inputs and the density of the material and what's required. So in terms of the upper limit, you know, we've done systems up to and over 1,000 tons per hour.
Thank you.
Yep. Looks like Don asked, what is the best location to feed fly ash back into a power boiler? He says high air velocities in a boiler is my concern. I might refer you to the boiler feed presentation, or if you have a specific application like this, to go ahead and we can have a discussion outside of the presentation on that. You know, it's really I hate to keep saying this, but it's going to depend upon a lot of different factors and what's going to happen. If high air velocities are going to be a concern, you know, we can use the expanded line to help lower the air velocity at a certain point and keep it to a certain limit. But since we calculate the velocity at the end, if he's got a certain maximum that it has to be, we can work backwards from that and make sure that the system will operate within your requirements. So Alan asks, how does differential pressure affect the pipe size? It's almost the opposite if you think about it. The pipe size, if you increase the pipe size, it's going to lower the pressure. If you think about air being in the pipe, if you have more area in there, you got less pressure. So we're really sizing the pipe based on the rate of material, the air to material ratio, and then checking to make sure that the selected pipe size is within our pressure limits that we need. So if we have say you want to use a 14-inch pipe, but the differential pressure used with your requirements there is going to be 10 psi. Well, that's too high for us, so we would increase to a 16-inch pipe, which would likely decrease the pressure within reasonable limits. Anybody else? You know, with our systems, we're going to have a small service factor built into there, but you're pretty limited to how much change is possible. Something people want to know, though we do design to an exact limit, there's a small safety factor there, so you might be able to squeeze out a little bit more. This, of course, is not recommended if you're planning on squeezing out more. We'd rather design to that size, but there is slight fluctuation possible. If nobody has any more questions, I'd just like to thank everybody again for joining in. Hopefully you learned something. Thank you.